Hello everyone and welcome to Education Foundation. And in today's video, we'll be looking at an introductory aspect to heat and work in thermodynamics. At the end of this video, we are expected to know what work is, what heat is, and the similarities between work and heat. So now let's talk about work. What is work? Take down work. That's the definition of work. Work can be defined as a transient form of energy that appears at the boundary between the system and its surroundings. In other words, it's that energy that is located between a system and its surrounding or environment. Now that we know the definition of work, let's go over to the derivation of the work formula that is used in calculations in thermodynamics. So derivation of work done formula. Work done is also called work. So we are now going to derive the formula. You should take note that work is equals to force times distance, that is x, F times x. But we should now recall that pressure that is P is equals to force that is F all over area. If we now make F the solid of the formula from the formula of pressure, force will now be equals to pressure times area. That is F is equals to P times A. That is PA. But now we should recall that work is equals to force times distance. So we are going to substitute the value of force, which is PA, into the work done formula, which is force times distance. So in other words, work will now be equals to PA times distance. Let's put this as equation 2. And let's put that our initial equation as equation 1. This is just to make reference easier for us. So now we should recall, another thing we should recall, number 2 thing we should recall is that area times, that's A, multiplied by distance, that's D, will be equals to volume, that is V. We know that volume is actually equals to length times breadth times height, or for a cube is equals to length times length times length. But we're not considering that in this case. We are just trying to derive the work done formula, and that is why we say volume is equal to area times distance. So what we are going to do is that we are going to substitute the value of A and X with V. So that will now give us this. Work done will then be equals to PV. That is pressure times volume. But we are not done getting the formula for work done yet. So our next process is to differentiate W with respect to V. Which will give us dW all over dV, which will be equals to P. So after we have gotten this derivative, we are now going to cross multiply. Cross multiply. This will now give us dW is equals to P dV. So what we are now going to do, that is the next step we are going to consider, is to integrate both sides. So integrating both sides, that is the integral of dW, which will be equal to the integral of P dV. So now that will now be equals to W is equals to the integral of P dV. But we should take note that the work done is then equals to the integral of V2 V1, where V2 is the upper limit and V1 is the lower limit of the integral of the function of P dV. That is V2 V1 P dV. So therefore, this is the formula for work done in a thermodynamic system. But we should take note of some of the following things before we go to the next part of the video. You should take note that the V is positive when the volume increases, and the V is negative when the volume decreases. So it's positive when the volume increases and negative when the volume decreases. So in some questions, you can see the V represented by a positive sign, that's a plus sign. Then you can see the V also represented by a negative sign, that is a minus sign. We should also notice that when it increases, that means when it's represented by a plus sign, it means that an expansion process occurs. But when it decreases, when it's represented by a negative sign, it means that a compression or a compression process occurs, or a system undergoes a compression process. Other things that we should take note of when we are talking about work done is that the work done in a system is interpreted as the area under a curve. So work done is interpreted as the area under a curve. So this is to simply say that the work done is equal to the area under a curve when we are trying to interpret the work done of a system using a graphical method or using our graph. We should also take note of the rate of work energy transfer, which is denoted by W with a dot on top. We should not forget this dot on top. It indicates the rate of work energy transfer, which is also called power. Let's put it in bracket. Power is then equals to work, that is then W. The work here is measured in joules, all over time. In this case, I'll be using T, but at times in some questions you can see the value of time changing, or you can see the value of time being represented by a small letter T or other values that the person or the question will choose to represent time with. So we should notice that, or we should take note that the rate at which work energy transfer is carried, or the rate at which work energy transfer is done, is known as power, and then such power is then measured in watts. So now that we have done with work, the definition of work, and then the derivation of work, we will now be going into heat. In our next video, we'll be looking at what is heat and then the similarities between work and heat. So if you found this video helpful, don't forget to like, subscribe, and drop your questions in the comment section below. Thanks for watching, and see you in our next video.